Let's look at how we can use 2's complement to perform arithmetic on both positive and negative numbers. And what we'll see is that it's a very powerful number system because we can actually perform subtraction using an addition algorithm. Okay, so we talked about 2's complement being the way that you find the 2's complement of a number is it's a two-step process. So the first one is you take 1's comp of the number, and second is you add 1 to it. And this works when you go from positive to negative or vice versa. And so let's just do a quick example. If I walked up to you and I said, I would like to represent, I want to know what the 2's complement code is for positive 6 decimal. And the first question you would ask is, well, how many bits is that? So let's do this in 4-bit 2's complement. So the first step of this is you need to find what the positive code for 6 is in unsigned or just in positive binary. And so what we'll do is I'll just 0110 is what the code comes out to be. So that's equal to positive 6. And you can use the conversion algorithms if you wanted to figure that out, but I just happen to know it by looking it up in the table. And so I'm going to take that, and now I want to find negative 6 in 2's complement. So the first step that I do is I take the 1's complement of everything, so I flip all the bits, and then step 2 is I add 1 to it. And what I have is 1, 0, 0, 0, 1, so I get 0 with a carry. 1 plus 0 is 1, and then I add 0, and then I have 1. So I get 1 plus 1 is 0 with a carry, and then I get 1, 0, 1, 0. So now that is going to be equal to negative 6 in 2's complement. Okay, so this is good, and what I want to do now is I would like to, the other thing that's very important when you do 2's complement is if there's ever a carry, you ignore it. So you never accommodate a carry. So this is not, so that's just the way it works, that you convert this code over, and if there ever was a carry, then what you do is you just ignore it and you look at that actual code. Okay? So let's take a look now at how we would go from a negative number into a positive number. So let's say that I came along and I said I have negative 5 in 2's complement, and what I want to do is I want to find what its 2's complement code is. Okay, so instead of going from given a positive number and finding it's negative, I'm given that I want negative 5. So the way you would do this is you would then say, okay, I want to know what positive 5 is, and then I'll convert it. So positive 5 in 4-bit binary would be 0, 1, 0, 1, and then what I would do is step 1, I would go 1, 0, 1, 0. Step 2, I would add 1 to it, so I'd get 1, 1, 0, 1. So 1, 0, 1, 1 is negative 5 in 2's complement. Okay, so that's very similar, but just given a different one. What if I gave somebody a code? What if you started with a code? So let's say you started with 1, 0, 0, 1, and you said, what is that in decimal? So the first thing you'd say is, well, what encoding technique did you use? And I used 4-bit 2's complement. So what that means is that you know that it's a negative number. So you have a negative sign for sure, and then what you're going to do is you are going to find what the value is, what the actual positive equivalent of that is, by taking the 2's complement. So what I would do is I'm going to take the 2's complement, so step 1 is I complement every bit, and then step 2 is I add 1 to it, and so I get 0, 1, 1, 1. Now this is positive 7 in decimal, so what I do is I take that value and I plug it in right here. So the answer is code 1001 is negative 7 in decimal. And I had to do that by first recognizing the sign and then finding the positive equivalent of it and then combining the sign back. Okay? All right, so 2's complement is a very powerful thing because if you think about arithmetic, one of the things that I can do is I can come along and I can say, if I have the ability to represent numbers as negatives, then I can actually perform subtraction using addition. And a simple example of that is, let's say that I had 6 minus 3, and the answer is obviously positive 3, but if I had the ability to represent a negative number, I could say that that's equivalent to 6 plus a negative 3. And this is very handy because when you build these logic circuits, it's easier sometimes to represent the codes as a negative number than it would be to actually build a subtraction circuit. So that's a very important thing when you come to minimizing logic. So this would still result in positive 3. Okay, so let's take a look at if this actually works. So what I'm going to do is I want to use 4-bit 2's complement, and I want to do this. So the first thing I'm going to need to do is I'm going to convert both of these numbers into 4-bit 2's complement codes. So 6 is going to be equal to 0, 1, 1, 0. And that's just the straight positive code. But we also need to convert negative 3. We need to find the 2's complement code for negative 3. So how do you do that? Well, let's come down here and I'll say what is negative 3. So the first thing I'm going to do is I'm going to give it the positive 3. So I come up with the code for positive 3. So this is positive 3 is equal to that. And then I take the 2's complement of it. So I go 1, 1, 0, 0. Step 2 is I go add 1 to it. So I get 1, 0, 1, 1. So the answer is that this is actually 1101 is what negative 3 decimal is in 2's complement code. So then I'm going to come back up here and I'm going to add negative 3, and that's equal to 1101, and I'm ready to go. So let's go ahead and add this using typical binary. So 0 plus 1 is 1, 1 plus 0 is 1, 1 plus 1 is 0 with a carry, 1 plus 0 plus 1 is 0 with a carry. Now we had a carry here, but in 2's complement arithmetic, we ignore this. We just always ignore that carry. The carry does not play any part in 2's complement, either negation or arithmetic. So what we're left with is 0, 0, 1, 1. Well, this is actually positive 3 decimal if you just convert that back. And so this subtraction actually worked. I was able to use addition, and I converted positive 3 to a negative equivalent, and I was able to use one operation, which was addition, in order to get the right value. So this actually works, and it'll be used later to kind of simplify things. There's one warning with this, and that is this concept of what we call 2's complement negation. Okay? So we're going to have 2's complement negation, or excuse me, 2's complement, sorry about that, overflow. And this refers to a problem. 2's complement overflow is not a carry. So that is the most common misconception. This is not a carry. What it is when the result is out of range. Okay? And a classic example of this is, let's add 7 to 7 using 4-bit 2's complement. Well, if I went and represented 7 in 2's complement, it would be 0, 1, 1, 1, and then I'd have 0, 1, 1, 1, and I would add them together, and the problem is this. 7 plus 7 is positive 14. That's the right answer. Positive 14 cannot be represented in 2's complement, because remember the range that we've been looking at for a 4-bit goes from negative 8 up to positive 7, so this doesn't fit. So let's take a look at what we would have. We would have 1 plus 1 is 0 with a carry, 1 plus 1 plus 1 is 1 with a carry, 1 plus 1 plus 1 is 1 with a carry, and then you would have that. So we would get an answer of 1110. Now what is that number? Well, who knows what it is? Let's find out what its positive, or let's find out what its decimal equivalent is. First thing is I know I got a sign bit, so I'm going to have a negative, and then I'm going to find what the absolute value is of this by taking 2's complement. So I will complement all bits, 0, 0, 0, 1, and then I'll add 1 to it, and I would get 0 with a carry, and then I'd get 0, 0. So I'd get 0, 0, 1, 0, which happens to be 2, so I'd get negative 2. So if you built this circuit, you would say 7 plus 7, and you would get a result of negative 2. So that's obviously incorrect, and that is what 2's complement overflow is all about. So 2's complement overflow is something that it's an independent check of whether the arithmetic operation was correct. So now we're sitting here and saying, well, how do you do that? How do you find if you did have 2's complement overflow? Well, you can do it by simply looking at the sign bits. Notice that we added two positive numbers together and we got a negative number. So you can actually build a circuit that just looks at the sign bits and says, if you're performing addition and you ever add a positive to a positive and you get a negative, then you had 2's complement. So it's a separate circuit that basically raises a flag and says, hey, you have a problem. You performed an addition and we have a problem, and then you have a separate system that handles that problem. Similarly, if you were performing subtraction, if you decide to build a subtraction circuit, if you had a negative minus a negative, you should have got a negative. Well, if you got a positive, then you have 2's complement negation too. So there's an algorithm in here that allows you to see if you had 2's complement negation. So there's 3 steps that you look at. So the first one is you have a sum of like signs, and the answer is the opposite sign. So positive plus positive gets a negative, or negative plus negative is a positive. Or if you have a subtraction of positive numbers from a negative number and the result is a positive, then that can't be. Or if you have a subtraction of a negative number from a positive number and the result in a negative number, then that's it. So these 3 conditions are what you can do. You can build a separate checking circuit. So the whole concept here is that 2's complement is a very powerful number system that allows you to represent sign numbers very efficiently. It allows you to do arithmetic. Not only are all the codes continuous within the set, but they are also in an incrementing order. It also preserves the rollover. And then you can also perform subtraction by using addition, as long as you keep in mind that there is a possibility that the result might be out of range of the numbers that can be represented with 2's complement, and that then is called 2's complement overflow. The final thing I'll warn you about is that 2's complement overflow is not a carry. It is not a carry. You can absolutely have a carry and the arithmetic worked, as in this example. We had a carry and the answer was correct. So 2's complement overflow has nothing to do with a carry. Okay.